It is possible to form alkynes via an elimination. And let's look at some of these reactions then. Now, previously we said that sp2 carbons are resistant to reactions like substitution and elimination. But, of course, there are ways around those resistance. So let's just look at an example here. So if we have an sp2 carbon, and we've got our leaving group over here, then we can bring in a relatively strong base deprotonate and perform an E2 on this. And it's possible to make an alkyne this way. And of course we'll have our protonated base. And our leaving group. Now, one of the reasons why this is less favored is because our bonds between the carbon and the leaving group are stronger when we have an sp2 carbon, because they have more S character. That increases the bond strength a little bit. And so they're less reactive. So if we would like to perform an elimination, we will need some more extreme conditions. So let's look at an example of that. So if we start off with this molecule here, which has a double bond right there, and I'm going to draw in the hydrogen for emphasis as to where that's going to be deprotonated. So we have a leaving group right here, which is the chloride. And if we try to do this with potassium hydroxide, we're going to need to heat this quite a bit. And let's see here, we need some methanol and dioxane solvent. Dioxane. And we're going to heat this, and we're going to let this reaction run overnight, which generally means about 18 hours, which is quite a while. And if we do, we can form this product in decent yields. I think it's over 90%. But these are some pretty long reactions under some fairly harsh conditions. To affect this transformation. Sometimes when we're using hydroxides as bases, we'll even need to turn up the temperature to around 200 degrees Celsius, which is in some cases not very feasible. So we'll need to look for a condition that can do this a little bit milder. In terms of the heat, we're definitely not going milder on the strength of the base. So let's examine what could happen if we use a stronger base, like sodium hydride or the sodium amine. So either NaH or the nucleophilic or strong base NaNH2. Right? These are very strong bases. If we use this in a reaction, we'll get our products much faster and at much lower temperatures. let's look at an example of this. Now in this case we made a terminal or an internal alkyne. Let's look at what would happen if we have a terminal alkyne. So we've got our leaving group here, some bromide, and we're going to need to do 2 steps on this. I'll explain why in just a moment. We're going to need 2 equivalents of our really strong base here. And we can run this in dimethylformamide at 0 degrees for about an hour. Which is in stark contrast to up here where we had to raise the temperature up to probably at least the boiling point of dioxane, which is about 100 Celsius. And we had to do that overnight. Now, we have step 1, which is going to deprotonate this hydrogen here, and then once we form the alkyne, it's going to deprotonate the terminal alkyne, because remember, those are acidic, and this is a really strong base. So we're just going to lose that proton. So in step number 2, we're just going to need to put that proton back on. So we just need a weak acid here, or maybe even just some water. And in this case, we'll form our alkyne. With the proton on. So, I'm going to draw the mechanism for this reaction, and in doing so, we should explain why we need 2 equivalents of our base and the acid workup. So, we'll just start right here, and we've got a hydride here. That's going to come in, steal the proton, and then cascade this through in an E2 fashion. That's going to make an intermediate. Now, I say that's an intermediate because, well, we're not really done with the hydride reactions here. So we're going to, even though this is the product, it's not going to stay that way for very long. We've got our hydride, that's going to come in, deprotonate, and we will get this, which is probably more appropriately called the intermediate. And then we have a negative charge right there. And then when we do our acid workup, right, so this is where the second equivalent of hydride goes. It goes to steal the other proton off of here, which we don't really want, but we can't really stop. So we're going to form really a carbon nucleophile. So if you wanted to use this in a nucleophilic reaction, you could at this point, but if we're just going for the terminal alkyne, we'll go ahead and continue this reaction. Of course, this is going to make hydrogen gas right here. So you'll have that bubbling out of the container. Maybe you won't notice it because of the amounts made. And then we'll add our acid workup. Which will form our product. So that's where the 2 equivalents are coming from. Now, it's not just possible to start from an alkene to form an alkyne, we could also start from an alkane that has 2 leaving groups on it. And there are 2 positions that we could have for those. And the mechanism is very similar. We'll just do consecutive E2 reactions, one to form the alkene and then another to form the alkyne. And then we may need a workup step in there. But I'm not going to draw the mechanism for these reactions. I'm just going to state that it's possible because we've already gone over some of the mechanisms. So if we have chlorides, they're on the same carbon here, and we choose a fairly strong base. This time we'll choose this nitrogen 1. We're going to need 3 equivalents of the base because we have 2 protons to remove, and then we'll also be removing the terminal alkyne proton. Now, if this wasn't terminal, we would only need the 2 equivalents because it would not have an additional proton to take. And we're going to have to heat this a little bit. And then we'll have a second step, which is just a workup to replace the hydrogen that's going to be lost to that base. And if we do that, we'll get a terminal alkyne. Just like this. Now, we could put both of the chlorides on one carbon, or we could use bromides, either one, halogens. Or we could locate the bromides on adjacent carbons. Like this. And this is a useful configuration because one of the reactions that we'll learn in the future, or go over in the future, is reaction of an alkene, and then we can add bromine over the alkene, and it adds 1 bromine to each carbon. And then this is a way that we can take an alkene and actually turn it into an alkyne by just adding bromine and then doing another elimination. So in this case, we'll just need some base, and we could use KOH if we want lower yields and longer reaction times, but if we do, we won't really need an acid workup because KOH is not really capable of deprotonating that terminal alkyne. So we can do that. And again, these could be chlorides, these could be bromides. There's nothing particularly special about that, but just note that they could either be on the same carbon or they could be on adjacent carbons. And in both cases, we could do 2 elimination reactions and then form our product. And just keep in mind the number of equivalents of our strong bases that we need. It's a little bit more than it might be initially expected, even though we really only want to remove either 1 or 2 protons. We end up taking the terminal alkyne proton in some case, if we have that available, so we'll have to add more equivalents. But this is how to form alkynes via an elimination reaction.